So let me now give a summary of the behavior of the periodically driven damped pendulum in the nonlinear regime. And here I'm following closely the treatment that's given in John Taylor's book in Classical Mechanics because it's very simple and it's very clear. So before I do anything, we have to also choose the initial condition. As we've seen previously, 3 and higher dimensional dynamical systems, the ensuing behavior depends sensitively on the initial condition. And what I'm about to present to you actually is initial condition dependent. But for convenience, let me choose the following initial condition, that phi dot of 0, the initial angular velocity, is equal to 0, but phi of 0 is equal to minus pi over 2. For the animations I'm about to show, the natural frequency of the pendulum is 1.5, twice the damping parameter is 0.75, the driving frequency is 1, and the time step is 0.025. So that means we're starting our pendulum. Here's the pivot point. The pendulum is inclined at an angle minus pi over 2 with respect to the vertical, and here is the pendulum itself. And we're starting at rest, so it's going to begin rotating counterclockwise. So when gamma is a little bit larger than 1, one finds that there is a short chaotic transient, but then eventually you settle to periodic behavior. Amazingly, as soon as gamma passes a critical value, which turns out to be 1.0663 ... First of all, there's a longer chaotic transient, but then the system settles into a 2-cycle behavior. And what I mean by a 2-cycle is that if I look at the oscillations of the pendulum, there'll be first a big oscillation, then a slightly smaller one. Big, small, alternating big and small. So this is the 2-cycle behavior. It's basically periodic, modulated periodic behavior. When gamma passes another critical value, which is 1.0793, again, longer and longer transients occur, but eventually you settle down to a 4-cycle. When gamma passes 1.0821 ... Eventually, the system settles into an 8-cycle. There is a sequence of period doubling bifurcations, just as in the case of the good old discrete logistic map. When gamma passes another critical value, 1.0829 ... there is chaos. That is that the pendulum never settles down into any kind of periodic behavior, and its motion is basically unpredictable. Interestingly enough, when you pass another critical value, 1.13 ... there is eventually the first appearance of a 3-cycle, just as in the logistic map itself. And finally, another amazing feature about this sequence of period doubling bifurcations, a chaotic window, the birth of a 3-cycle, is that all of this phenomenology mirrors exactly what happens in the case of the discrete logistic map. And in particular, this number delta that measures the ratio of window sizes. So the range of behavior for which a 2-cycle occurs is between 1.0793 and 1.0663. And then there's a smaller window where the 4-cycle lives between 1.0821 and 1.0793. And if I measure delta, which is the ratio of successive window sizes, so this would be gamma n minus gamma n minus 1. So that's the window size of a particular period 2 to the n, and compared to the window size of the next higher period, gamma n plus 1 minus gamma n. As I go further up in the periodicity, the size of the window gets smaller and smaller. So the numerator is bigger than the denominator, and then the limit as n goes to infinity goes to this universal number, this Feigenbaum constant, 4.669 ... That was the same as what we saw in the discrete logistic map. So there is a one-to-one, at least phenomenological correspondence between the amplitude of the forcing and the parameter A in the discrete logistic map. Xn is equal to A xn 1 minus xn. So amazingly, this period doubling bifurcation and the ensuing chaotic window, and then the 3-cycle with this ensuing period doubling bifurcation on top of that, what we see in the nonlinear driven pendulum is the same as in the logistic map. So it's incredibly beautiful phenomenology, but in some sense we can understand it from the mathematics of the logistic map itself. One other thing I just want to mention as a postscript is that this phenomenology that I've outlined here holds only for the specific initial condition of starting at rest with the pendulum at minus pi/2. If one has a different initial condition, there is different phenomenology for the behavior as a function of gamma.